right? So, but before that, I have to finish. We started the concept of conservative and non-conservative forces. Ji Aman?
Sir, sorry to interrupt. Magar, can the assignment deadline please be extended to Sunday?
It was already extended. I'll see. Let me talk to Dr. Adam.
Actually, we're having mids, so it's very hard to take time out to do it.
Okay. So conservative forces. So this is what we said, that the work done by a force is simply the dot product of the force with the path from point A to B. Okay. This is work. Okay. And as you can see, this integration suggests that work may actually depend on the path that you travel along. Okay. And it was in a way contradiction, because that was our original motivation. Remember the example, because we cannot solve the Newton's law because we found a situation where force depends on the position. Okay, force depends on the position, so we cannot specify the force, and without specifying the force, we cannot find the position using this equation. But here we are again. It seems a circular journey, that here we have, and we may have a situation where force depends on the path, and there are cases where it does depend on the path. Okay, but a huge number of forces, a big group of forces that we would be dealing in this course and in general as well, which in those forces, the work done by the force does not depend on the path that you take. So what it means is, let's say that you have an object, right? And you have an object here at the origin, okay? And you want this object to move to a point B. Let's say you have an object sitting at origin at point A, and you want this object to move to point B. Okay, there are two paths that we can consider, but there are in fact, how many paths are possible? How many ways, different paths that you can take from A to B? Anyone?
The infinite paths.
Infinite paths. There are infinite ways of going from A to B. Okay, we're just looking at the two simplest well-behaved paths. Okay, and now if we calculate the work done, so let's make some coordinate system, and some, let's say this is length 1, this is length 2, so this would be length 2, and this is length 1. And let's consider that the force field, if I may use the word, the force that we are considering this work in or by is the gravity, is the force of gravity acting on the object. Now if we first choose this path, let's call it path 1. Okay, if you take path 1 and calculate the work done along path 1, so let's chop the path into two pieces. Let's call this A to C. Okay, first calculate the work done from A to C. What would be the work done? So let me write the vectors for the force. The force in this case is minus mg ex, and the distance in this case from A to C is ds, if I may write, is simply L, sorry, ex. So what would be the work done when you move the object from point A to C? Anyone, please quickly in chat. Dot product between these two vectors. Dot product between these two vectors.
Sir, MGL1 होगा.
Dot product between those two vectors, please. This is pointing along EX. This is pointing along Y axis. So in fact, I don't need to write DS. Simply S would be better because we don't need to do the integration. So S. So the dot. What is the dot product between F dot S here?
0.
0. So no work done. Okay. The force and the distance make a 90-degree angle. Okay. No work done. 0. So this is the work done from A to C. Okay. And now let's consider work done from C to B. The first path, the path 1. Okay. So we still have the same force, but now the distance S is different. Okay. What would be S in this case? S would be L2 EY. Okay. L2 EY. Now dot product between this and force remains the same. So what would be the work done?
MGL2, negative MGL2.
Negative MGL2. Okay. And the total work done from going A to B, you just add it. Okay. And the total work along path 1 is negative MGL2. All right. And then now we choose path 2. Okay. We go along this path. So what would be the work done from A to D, let's say? Work done from A to D, the force is the same and L2 is the same. Okay.
Negative MGL2.
Negative. So work done from A to D is negative MGL2. And how about the work done from D to B?
0.
0, because the force and the displacement are orthogonal. Okay, 0. And what is the total work done along path 2?
Minus MGL2 EY.
Minus MGL2. Work is a scalar. Okay, although it depends on two vectors, but it's a dot product between two vectors. It's a scalar quantity, no direction, right? So the work done on along path 1 is equal to, this is not the most general case. This was an example. Okay, and work done along path 2 are the same. All right. So this is a sign of a conservative force. When work done from a point, given point to another given point does not depend on which path you take, and you can show that you can take any path you like, the work done would be the same. All right. So gravity is a conservative force, but this is not, this gravity is a conservative force, but sometimes it is not. You have to be careful. When is it not? Because here we are assuming that G does not depend on the position. Close to the surface of Earth, we take the small g as constant. Okay, and far away from the surface of Earth, G again is the gravitational force, is again a conservative force because it does not depend on position. But there is a certain situation at a certain scale where G does become dependent on position. And when that is the case, then the gravity may not be a conservative force. Okay. But in general, you can assume, and the problems that we would be doing in this course, you can take gravity as a conservative force. So this is a conservative force. When the work done depends only on the position of the object at the end point and at the beginning, and it does not depend on the path, in which path information, where how you get to that point. Okay, is this clear?
Excuse me, sir, I had a question. आपका जो gravity है, आप ये कह सकते हो कि gravity आप outer space में भी conservative force के तौर पे नहीं लोगे क्योंकि वहाँ पर भी it depends on the distance from the earth की gravitational force कितनी होगी?
नहीं, outer space में away from Earth, you can take it as a conservative force. because then the acceleration does not depend on the position.
Right.
So now an example of a non-conservative force. All right, so now let's say that you have a surface and we are looking from the top, okay? And on a horizontal flat surface, we are looking from the top, and we have an object sitting at A, okay? And we want to take it to point B. Okay, and we take two paths, relatively simplified paths. Okay, we go to B directly, or we go to B via this path, path 1 and path 2. Okay, no other force is acting on it except the force of friction. Only the friction force is acting on it, right? Now, when we move the object in this direction, what would be the direction of the friction force when we move the object from A to B?
Friction will be B to A.
Friction would be in this direction. So if I choose a coordinate system like this, X and Y, all right? And the length between A to B is L. Okay. Can I write these vectors? The force now is minus F EX, right? And what would be the S then? Would be L EX, all right? So now work done from A to B, okay, along the first path, path 1, is what?
Minus FL.
Minus FL, yes. Okay. So because friction is always opposing the motion, it's always in the opposite direction of the motion. Nearly always work done by a frictional force is negative. Okay. So this is the work done by the force of friction when you go from A to B. Okay, now let's go along the second path, okay, and calculate first the work done from A to C. Okay, this is work done along path 1. Okay. Now let's calculate work done from A to C. Okay, the force of friction now changes, okay, because we're moving from A to C. The force of friction in this case, so this is the case of AB. Let me make the AC. So what would be the force of friction now?
Positive FEY.
No, negative. Yes. So FEY, positive. Very good. And what about S now? Let's call this small l. The width.
So negative LEY.
Minus LEY.
Minus L EY. All right. So what would be the work done then?
Minus FL.
Minus F small l. Okay. And how about the force, the work done from C to D now? C to D. So what is the force now?
Negative FEX.
Negative FEX. And what is S?
L.
LEX, right? Because you're moving along the positive axis, right? So the work done from C to D is now
Negative FL.
negative F capital L, all right? And what about then D to B? Okay. First the force, Force would be positive Fey. No, negative Fey,
Negative.
because it's opposing the motion. And what is S? Small l Ey. Okay. This is positive, this is negative. So what would be the work done from D to B? Minus FL, right? And what would be all the work done along path 2 would be minus FL plus 2L. All right, यही होगा ना? So this was if we went along path 1, and this would be the work done if we went along path 2. So you see that? So you see any difference?
Yes sir, वो path 2 पे जो वो work done है वो ज़्यादा है in
Yes,
comparison to path.
yes. So the work done depends on path. That's why the force of friction is a non-conservative force. Okay, that's the definition of conservative forces. For a conservative force, work done does not depend on the detail of the path. It only depends on the endpoints. Okay, work done by a non-conservative force depends on how you get to a point. All right, that's the main definition. Is it clear to everyone? Yes, yes.
डीबी के अंदर जो एफ है वो माइनस क्यों है?
ये वाले पाथ में, because you're moving upwards. So you are moving upwards, so friction इस direction में होगी, it just opposes the motion always.
जी ठीक, थैंक यू।
ठीक है. So gravity in general is a conservative force. Spring force is a conservative force. Electrostatic force, the attraction or repulsion between two charges, whether they are opposite charges or similar charges, that is also a conservative force. In general, the central forces are conservative forces. What are central forces? Do you know what are central forces? Central forces are the one which depend on the mutual distance between two objects. Okay. Forces which have this functional dependence. Okay. On the distance between 2 points or 2 objects which have this type of, now you know the Coulomb force has this type of dependence on separation between two charges. Gravity has this type of dependence on attraction between two masses. Okay, these are called central forces. Central forces can be shown more generally to be conservative forces. Work done in a central force is always independent of the path. Okay. Okay. Any question
Sir,
about
मैंने एक
this?
चीज हमने
जी
जो
जी.
force दिया, sir, we've taken it to be equal to the friction, but shouldn't it be in the opposite direction to counter the friction?
Which force?
Sir, जो अभी हमने example किया है path 1 and path 2 का. So, sir, shouldn't the sign be the opposite for the force because it needs to counter the friction?
नहीं नहीं, देखें ये तो मैंने टोटल फोर्सेस लिखी है ना जो एक्ट कर रही हैं. ठीक है, वन ऑफ देम इज फ्रिक्शन, देयर इज नो अदर फोर्स. ऑलराइट, एंड ये मैग्नीट्यूड है फ्रिक्शन का. F is magnitude of the friction and the direction, so it has to counter the motion, and motion is not in the same direction as the friction.
Okay.
ठीक है ना?
Thank you, sir.
ये ऐसे भी तो इसको लिख सकते थे ना, if you want me to write it explicitly. So mu mg, ये normal force है. ठीक है, mu times normal force is the magnitude of the friction, and then I had to add a direction. All right. So its sign would change depending on the direction of motion. Friction is a tricky force to deal with because whenever you have to choose the sign for the friction, the direction of the force of friction, you always have to look which direction you're moving. So it always opposes motion.
Okay, thank you, sir.
So this is all about the conservative forces. Now we are going to move on to another concept, very important, the potential energy. Now let's say that we have an object hanging above the surface of mass m, and it is, let's say, 5 meters above the surface of Earth. Okay. When we allow this object, once we release this object, what would be the work done by gravity?
mgh.
Mgh. So if I want to write it, that would be, let's say it's 1 kilogram. Okay, that would be 1 times mass times the acceleration times the height. Okay, and if mgh is not clear to everyone, what it means is that the force is acting in this direction, the gravity, and the distance is also in this direction. They are in the same direction. So the final work would be positive, and it would be simply, if you want to write it, this would be the proper way of writing it. F equals minus mgey, and the distance in this case would be minus 5 ey. Okay, if you take the dot product, you get this simply mg times 5, and the minus of both, because both vectors are pointing downwards, would become plus. So you plug in the values and you get how much work?
50.
500. But 500 what?
So 550 होगा ना?
Oh, sorry, yes, 50, yes. Yes, 50, yes. So 50 what?
Joules.
Joules. So the units of work, let's settle that. So work in general is F dot S, right? And that is newtons meter. So 1 Newton meter, when you use 1 Newton force and you move an object by 1 meter distance, doesn't really matter how fast, how slow, okay? So long as you move the object 1 meter using a 1 Newton force, that means you have done 1 joule work. Okay, so named after an English physicist. And you can always write the main the definition in the fundamental unit. So what is Newton? Newton is kilogram meter per second square times meter. So that would be if you want to write the dimensions. All right. One more question. What are the units of energy? The kinetic energy, let's say, we have been dealing with. The units of energy.
Sir, वो भी joules ही होते हैं.
सर वो kg मीटर स्क्वायर पर सेकंड स्क्वायर आ रहा है.
Okay, that's a different system. We're talking about the system international, SI. So you see the definition, okay? We said that work done by a force moving an object from a given point to another point is equal to the difference in the kinetic energy, change in the kinetic energy, okay? Let's say initially kinetic energy is 0. So what is work done? Equal to the final kinetic energy of the object. All right. So kinetic energy cannot have units different than work. So the energy has same units as work, joules. Otherwise, this equation or the work energy theorem would not make sense. All right. Now this was about the unit. So we have 50 joules. Now let's say that I have another object at 10 meters. Okay. What, and it's still the same weight. I drop it from 10 meters. What would be the work done? 100 joules.
100.
Right? And now if I drop it from 20 meters, then what would be the work done?
200 joules.
Yes. Okay. 200 joules. Okay. So now according to the work energy theorem, what would be its kinetic energy when it hits the surface of Earth?
200 joules.
Ji, 200 joules in this case, 100 joule in this case, 50 joules in this case, right? So its energy really depends on the final energy, really depends on where we throw it, right? Right?
Yes.
So the higher the position, the more kinetic energy at the end of the journey it has, right? That would be the kinetic energy, 50, 100, 200. The higher you go, the more kinetic energy it hits. Okay, now let's do the opposite of it, okay? Let's say that the object is on the surface of Earth. Okay, this here. Now you want to lift it to 5 meters. How much work do we need to do?
Negative 50.
Negative 50 joules. We are working against gravity. Okay, we're moving the object in the opposite direction of the force. Okay, so we have to do minus 50 joules. If we want to lift it to 10 meters, then we need to do how much? Minus 100 joules. Okay, and then if you want to do it to 20 meters, then you need to do 200 joules. Okay, now see two pictures together. In this case, you release the object and you get a final kinetic energy, which really depends on where you release it. See this picture. The higher you want to hang this object, take this object, the more work you need to do. Okay. Now, doesn't it give you a feeling that this is a way of storing energy into the object? Because once the object is here, if you release it, it's going to have 200 joules kinetic energy when it hits the surface of Earth. It has no kinetic energy here. You're just holding it. Okay? So the process of lifting up, it means we are supplying energy to this object. We are taking it to a position. And then depending on where you take it, once you release it, we get the energy back. We get the energy in form of the kinetic energy. Okay? So this is a way to see that when an object is at a certain position, depending on its position, it has a potential, it has ability to do work. Okay, and higher the position in this case, it can be different relationship. Higher the position, the more potential it has. Without releasing, just looking at these three objects, just looking at their positions, you can tell that when I release this object, when it hits the surface of Earth, it would have more kinetic energy. It would have done more work. Okay, so it means that this has more ability to do work, this has less ability to do work, and this has even lesser ability to do work. Okay. There is a new, I'm sure you know that energy can come in different forms and it can change between forms. So there is another form of energy. One is the kinetic energy, that and if an object of mass m is moving at half mass times the square of its speed. If an object is moving with a certain speed, then half mass times the square of its speed is its kinetic energy. But here you see that there is another type of energy, okay? The ability to do work, okay? Due to its position, due to the position of the object. And that energy is called potential energy, as the name suggests. It's the ability to do work. The more ability to do work an object has, the more potential energy it has. The less ability to do work an object has, the less potential energy it has. For example, if the object is resting on the surface of Earth, it cannot do any more work. You just release it and it would be there. Okay, so it has zero potential energy. And if you have an object at 200 meters, it can do, sorry, at 20 meters, it can do 200 joules of work, okay? It means it has that potential. It has the potential to do 200 joules. That means its potential energy is 200 joules. Does it make sense?
Yes,
Or
sir.
is too abstract?
सर इस एग्जांपल से हमें वो वाला भी हमारी स्टेटमेंट नहीं प्रूव हो जाएगी वो कंजर्वेशन ऑफ एनर्जी की, क्योंकि जब वो मैक्स साइड पे है तो उसकी पोटेंशियल एनर्जी मैक्सिमम है, उसके बाद वो जब नीचे आता है तो उसकी मैक्सिमम पोटेंशियल एनर्जी रीचेस टू जीरो एंड काइनेटिक एनर्जी रीचेस टू इट्स मैक्स वैल्यू. तो ये
Yes, we'll get to that. We'll get to that in a minute. Okay, yes, but yes, you're right. All right, so now let's extend this further. Okay, so let's say that you have an object from the surface of Earth at y2 distance. Okay, that's the height, and it has certain mass, of course. Okay, and now, or even better, let's say that it's initially not here. Let's say it's initially somewhere here. Okay, at distance y1. Okay, and it has a certain mass. Okay, with respect to the ground, with respect to this point, okay, what is its potential energy, or what is its ability to do work?
mgy1.
mgy1. So it can do mgy1 work if you release it. Okay? And this is due to its position. This much work it would do. I mean, this if you just calculate the work done by the object once you release it, an object of mass m in the gravitational force at distance y1, this is how much work it would do. Now imagine if the object was at y2, so what would be the work done if you release it from here?
mgy2
हो जाएगा.
mgy2. How about if you release the object from here to here, bring it from this point to here, what would be the work done then?
y1 minus y2.
y1 minus y2. Okay, so this would be the work done. Okay, so this is very important, that it really depends on energy. Potential energy is always defined from a reference point. Okay, so when it is at my1 and we are looking at its ability to do work with respect to ground, then this is the amount of work it can do. When it is at mgy2 and we are looking at its ability to do work while getting to the ground, this is the work it can do, and this is its potential energy. Okay, and when we are looking at its ability to do work between this position to this position, then this distance, which is y1 minus y2, is what gives us its ability to do work. So this is very important, potential energy. Okay, now if this is the potential energy, okay, then what is this? What is this?
Change
in
in
potential energy.
What is this?
The potential energy like a midpoint या कितनी point
Change in the potential energy.
Yes, change in the potential energy. This is the change in the potential energy. But one more thing, when is the potential energy higher? And
At
when is the
Y1.
potential energy? Sorry?
Y1 पे
This one is larger and this one is smaller.
smaller.
Okay. So it means when you, what is the initial potential energy of the object, mgy1, and what is its energy when you get to this point? So you have to compare this quantity with this quantity. Okay, this one is larger, right? This is your initial potential energy, and this is the potential energy when you get here. So what have you done? You've decreased the potential energy. You have decreased the potential energy. So we established this relationship in the work kinetic energy theorem, that work is proportional to the change in kinetic energy. Okay. It turns out that work is also proportional to the change in, and if I could just call it U, the potential energy. Okay. So you could write this, for example, U y1, the potential energy at y1, minus U, the potential energy at y2. All right. All right. And the only difference is that if you look at, if you apply this theorem, what is the initial kinetic energy when the object is here? 0.
0.
0.
And when it goes here, its kinetic energy has increased, right? As it goes further down, its kinetic energy increases, and its potential energy decreases. So work done by the potential energy is actually proportional to the negative change in the potential energy. Okay. And the difference, this negative sign, comes from the fact that if kinetic energy increases, kinetic work done by, in this particular case, the work done is equal to the positive change in the kinetic energy. Okay. And work done by moving the object along the same line at the same, between the same 2 points, is equal to the negative change in the potential energy. Okay. So now minus delta U and delta K are equal to W. So that means I can write change in kinetic energy is equal to minus change in potential energy. Okay. This equation underlines the interconvertibility of the two energies. Okay. The kinetic energy increases by the same amount potential energy decreases. I can also write this as delta K plus delta U equals to 0. Okay. The sum of the change in kinetic energy and the potential energy is always 0. So kinetic energy changes by equal amount, by it increases or decreases by the same amount in the opposite direction, so that their sum is equal to 0. I can also write this equation as delta K plus U equals 0. Now these are not change in the energy. This is the total kinetic energy and total potential energy. So what does this equation signify?
Change in
Total
energy.
energy system. Total energy
So
system.
this is, so this, now this is kinetic energy of the system, right? Of the particle. This is the potential energy. K plus U is the total mechanical energy of the system. The total?
So total energy remains constant.
Yes, the total mechanical energy of the system is a conserved quantity. It remains constant. Total mechanical energy, be careful with the language. Okay? So the total energy is a conserved quantity. It remains constant. It can change between 1 and 2, but their sum remains 0. And you can verify in this example, in the previous example, or you can come up with it. And this law, the conservation of energy law, is much more general. This here we are only seeing the conservation of mechanical energy, but the energy is conserved for the other forms of energy are conserved as well if you have them in the system. So that conservation of energy is universal, and until today, we have not found a single exception where the energy is not conserved. This is very fundamental. Okay? This goes beyond mechanics, the conservation of energy. But this here you're seeing is that by introducing the concept of potential energy, we are able to get to this very fundamental law that energy is conserved. Mechanical energy of a system is conserved. And if it is not conserved, that means we have not taken into account some channel where energy is entering the system or exiting the system. So if you have a closed system where no energy is entering into the system or getting out of the system, then the energy would be, mechanical energy would be conserved. Okay. Any questions about this? So that you could also write K plus U equals constant. Yes.
सर ये वर्क डन नेगेटिव पोटेंशियल चेंज इन पोटेंशियल एनर्जी के कैसे इक्वल हुआ?
मैं ये कह रहा हूं कि जो आपकी जो वर्क डन है that would be equal to the negative change in potential energy, because potential energy decreases as if you're getting something out of the system. Okay, you're getting the potential, its ability to do work out of it. Okay, so the kinetic energy is, the work is equal to change in kinetic energy, but work is equal to the negative change in potential energy, because kinetic energy increases as you go down. Okay, the potential energy decreases. That's what this negative means. Okay.
ठीक सर.
So here is, so this also means, for example, this equation, that this also means, for example, if initially K1 is the kinetic energy of the system and U1 is the potential energy of the system, at a later stage, when system has moved, okay, when the system has moved and its kinetic energy has changed, this is only possible if its potential energy has also changed. Okay, and the new configuration, the sum in the new configuration would always be equal to this sum in the initial configuration. So the sum of the initial kinetic and potential energy is always equal to the sum of the initial final kinetic and potential energy. And an example like this, you can work this out. For example, if you have a basin that looks like this, okay, and let's say that this is L, this distance, all right. So if you release a ball here, if you have a ball here, what is its potential energy?
MGL.
MGL. Okay, you release it, you let it roll down. Okay, so what would be its potential energy when it gets here? Zero. And what would be its potential energy when it keeps rolling up and gets here?
Keep on increasing till MGL minus MGL.
Okay, MGL, it has, again, the potential energy is equal to MGL. So what is its velocity here when it reaches this point? Zero. So its kinetic energy would be zero. Okay, what would be its kinetic energy here? 0. And in between these three extremes, when it is here or here, it would have both a bit of the potential energy and a bit of the kinetic energy. And as it is moving down, its velocity is increasing, right? Its velocity is increasing. And here it would have the maximum velocity. So all the energy would be equal to its kinetic energy. So let's say that its total energy is given by this quantity E. Okay. In the very beginning, the total energy would be equal to just mgl. Okay. At this extreme, its total energy would be equals to k. And then at the other extreme, its total energy E, the total mechanical energy would be again equal to mgl. All right. So this underlines the interchangeability of the energy. Okay. So if you plot, for example, such a case, and on this side, let's say you have time, for example, or the position, whatever, doesn't really matter. In time, the total energy remains at E. Okay. And let's say that you also have the potential energy curve. The potential energy would go to from maximum to 0 in some form. You'll have to, and then it goes to maximum again. Okay. What is the kinetic energy initially? 0. It goes to maximum, then it goes to 0 again. Okay. Sum of these two graphs, one is the potential energy and the other is the kinetic energy, would always equal to this quantity here, E. And it's true at any point. Any point, and there would be a point where they would have the kinetic energy would be equal to the potential energy. Okay. These points.
Sir, the sum would be equal to E.
Yes, U plus K would be equal to E. Otherwise, energy would not be constant. So this total mechanical energy remains constant. Although this is a dynamic system, so the object is changing. Let's say this frictionless, there is no friction. So once you roll it, it keeps rolling back and forth, keeps rolling back and forth. So this is what keeps happening. And potential energy goes to kinetic energy goes to potential energy, and total energy remains the same. Okay. Now in reality, this does not happen. If you switch on friction, what happens is that in time, the total energy would keep decaying. Okay. Does that mean we are violating the conservation of energy? Hmm?
It is used to overcome the friction. It's not
Yes,
getting-
the energy is leaking out of the system in terms of heat and friction. So to overcome the friction, the energy is being spent to do negative work against friction. Okay. And that energy is leaking out of the system. That's why the energy is going out, and this would slow down and get to rest. Okay. These oscillations would become smaller and smaller and smaller. Any questions so far? Okay. So what is the relationship between potential energy and forces? Okay. So since we said that the work is equal to negative change in the potential energy, okay, that means, let's say that the final energy U2 minus U1 is equal to work. Okay. So let's say this is your final energy and this is your initial energy, and their difference is negative of their difference is equal to work done. Okay. And let's say that the initial energy is 0. Yes, we can choose that. Fine. We can have a situation. Then work is simply U2. And since That's my final energy. So I can just drop this notation and let's say W is equal to minus U. Okay. So now we know that work is this. And I'm considering the case of gravity. You can consider any force. Force times the distance from 0 to y is equal to minus u. Okay. Or I can just invert this equation and write it like this. U is equal to minus 0 to y mg dy. Okay. So if you carefully look at it, u is related to the force through this integral. Okay. 0 to y, and this is force, right? F dy. So the potential energy is related to the force, okay, in this way. Okay. But they we did that in calculus. We can also invert this equation and write like this. F is equal to negative the derivative of u with respect to y. So if you know the potential energy or potential energy function, to be more precise, then you can calculate the force by just taking the negative derivative of the potential energy is force. Right? So you can take a very simple example. Let's say, what is the potential energy? If an object is sitting at distance y from the earth, what would be its potential energy?
mgy.
mgy.
नेगेटिव mgy होगी ना?
नहीं, potential energy तो mgy ही है बस, not negative, positive. Okay, this is the potential energy. So now if you take the derivative of that mgy with respect to y, what you get is F is equal to minus mg. Okay, and it also gives you the sign, gives you the direction of the force. Okay, in this direction. Okay, now let's do another example of this relationship between force and potential energy.
ये फॉर्मूला वैसे प्रूव क्या करता है? F is equal to minus mg.
What we are proving is that if you know the potential energy, okay, you can find out the force. But I forgot to say that. Let me say it now, that you can only associate potential energy with conservative forces. You cannot write a potential energy for a non-conservative force. For friction, there is no associated potential energy for the force of friction. For any non-conservative force, okay, drag force or any other non-conservative force, you cannot write a potential energy. Okay, so you cannot drive the force from a function, a potential function. Okay, and this is what it means. Okay, so this is the basin again. Okay, and let's say it's this way. Okay, and this is L. Okay, now this basin has a certain, and this basin is in fact the potential energy surface or the potential energy curve. Okay, this curve is U, x and y. Okay, depending on the position of x and y, it has a value. So potential energy is maximum here, is 0 here, and then is maximum here, and then it has some intermediate value in between these extremes. Okay, so this is the potential energy curve. Okay, now without knowing the functional form, all right, so I'm saying that force is partial over, sorry, or du over dx. All right. So you could just write it in one dimension to make things simpler. U of x. Okay. Now look at this curve. You have practiced with derivatives. What is the derivative of this curve here?
Zero.
At the very bottom.
0.
So what would be the force then?
Zero.
0. So what would be the derivative of this curve here at this point? Some non-zero value, right?
Yes, sir.
Some non-zero positive value of the derivative, right? So let's call it small f, or let's call it whatever you like. F. Okay. Let's say that is the positive value of the derivative f. Okay, and negative sign. So then what does it tell us? It tells us that as you're climbing up the hill or sliding down, the force acting on this object, if this is your axis, is in this direction. Okay. Some positive force, and that force gets to, as you go higher up, it gets maximum. So as you go up, the force is 0 here, then the force becomes larger and larger in this direction. A larger and larger force is acting on it due to this potential energy. Okay. Then if you go here, at this point, the derivative would be negative, right? And a negative and this negative, when they multiply, the final form of the force becomes positive. So that means the moment you cross the valley, the force changes its sign. It's acting in this direction and its magnitude increases. Okay. So this is how the force and potential energy are related to each other. And the negative sign always tells you which direction the force is acting due to a given potential energy surface or a potential energy function. Does it make sense? For example, we haven't really done many examples, but let me give you this. Let's say that this is the force. Oh, sorry, this is the potential. Can you quickly find the force due to this potential? Please do it as an exercise quickly.
Minus
K.
half square.
Yes.
Not kx. Look at the relationship.
Minus kx.
Minus kx. So this is the potential energy or the potential associated with the spring, because this is, from here you recognize that this is a spring force. This is the potential associated with the spring force. All right. But you cannot write this for a non-conservative force. This is another sign. If you see a potential energy, a potential for and then you can drive a force from it, then you don't need to worry about it. You're always safe to assume that force is conservative. Non-conservative forces do not have an associated potential energy or potential energy functions. And in this case as well, if you plot the potential, this u half kx square, what kind of plot do you get? You get this kind of plot, right? Right? Now at every point, When x is positive, let's say this is 0. When x is positive, okay, when you are in this region and you take a derivative and k is positive, x is positive, what is the direction of the force here in this
Negative.
region? Negative. Force is acting in this direction. Force is trying to restore the object back to the 0 position. Now, when x is negative, and you take the derivative, then this you get this negative from the derivative. K is positive, x is negative. What is the direction of the force?
Positive.
Positive. So the moment you cross the mean position on the other side, the force starts acting in this direction. And larger the distance, larger the force. Okay? The force changes its direction and tries to restore the object back to the mean position or the equilibrium position. Okay, this is the end of work energy and the conservation of energy. And now we're moving on to something new. And this would be probably definitely the curriculum that you would have in the mid up to this point, but we finished today. And then so far the summary, except for formalism and other things, there are two fundamental things that we have learned so far. One of them is Newton's laws of motion. And the second is the conservation of energy. Okay. And these are two very fundamental results in physics, in classical physics particularly. And of course, the conservation of energy is more general. It goes, and of course, Newton's laws do not stand when you go to small scales or when you go to relativistic speeds, but the conservation of energy does stand everywhere. So that's why it's more universal, more general result. And it applies to all forms of energy. So this is it. Now we are going to learn. So far, using these fundamental laws, we have been treating objects as point particles, whether it was a human being, whether it was a car, whether it was a truck, whether it was a planet, or whatever object we had, we have been just treating them as point particles. But you know, in reality, objects are not point. Even this chalk is not point, okay? And when I throw it, it is not only executing the translational motion. It's going up and down, yes, but it also rotates. Okay, any object that you have, it has other forms of motion. Okay, and simply treating an object like a point is a great simplification. It's easier to understand and establish and apply the laws of mechanics, but it's not very realistic. Okay, a more realistic situation is that when we consider full objects and then we look at their motion, but then this becomes very complicated to deal with. So what we can do is we can take a finite sized object, a realistic object, and divide it into small parts. And take each small part as a point. So an object is nothing but a collection of points. And we have already studied the motion of points. Okay? So we take our concepts that we have developed for a point, and then we take a finite object, divide it into small points, and then apply our laws to one point, okay, and then sum them. Okay, sum all those equations, create or if you want to use, if you want me to use more technical term, just integrate it. So we choose one point on this object, we find this motion, and then we find the motion of another object, another point, and we sum all these equations. Okay, we integrate and we find the motion of a finite size object. Okay? And that is when we try to complicate physics. So for the sake of understanding, we were applying into unreasonably unrealistic but simple systems. Now we have to apply the physics reasonably realistic. They're not fully realistic. And this physics that we would be studying now is called system of particles. So we would be studying now system of particles. We were doing one particle. Now we have to generalize it. Okay, we would be studying now system of particles. And of course, when the objects move, they also rotate. Okay, so first we would develop some formalism how to quantify the system of particles, how to represent the system of particles, and then we would study any additional motion that they may execute while they move in addition to the translational motion. So far, we have been just considering the translational motion. We did not consider the rotation, but objects rotate as well as they move. Okay, so with this, thank you very much. And if you have any questions,